My name is Akshat Pardesi, and I am delighted to serve as your MC for this momentous event. Today, we have the unique privilege to dwell into the forefronts of knowledge, visionary ideas, and groundbreaking research within the realm of electrical and electronics engineering. The RDCAP Conference 2023 is a stage where industry luminaries, accomplished scholars, and dedicated professors come together to impart their wisdom, fueling our collective passion for the remarkable field we all share. But before we set sail into the sea of knowledge that awaits us today, let me introduce you to our esteemed individuals who will be guiding our journey. Let me present to you Dr. Ayan R. Peterson, Dr. Hasmat Malik, Dr. Ankur Balian, and Mr. M. Zafar. We eagerly await the knowledge and guidance these brilliant minds will bring to our upcoming session. Now, let us embark on the RDCAP 2023 conference. We hope you will enjoy the enlightening sessions and take full advantage of the opportunity for networking and collaboration that lies ahead. Thank you for being a part of this exciting event, and let us make today a memorable and educational experience for all. Without further ado, let us introduce our first speaker, Dr. Ayan R. Peterson. Dr. Ayan was born in Victoria, Australia. He received a PhD in electrical engineering in 1984 from the University of Rochester. From 1983 to 1985, he was a postdoctoral fellow at the Australian National University. From 2017, he has been a professor at the Australian National University in the School of Engineering. He was the interim director of the School of Engineering at the Australian National University from 2018 to 2019. From 1985 until 2016, he was with UNSW Canberra, where he was a Scientia professor and an Australian Research Councillor Laureate Fellow in the School of Engineering and Information Technology. He has previously been ARC Executive Director for Mathematics, Information and Communication, Acting Deputy Vice Chancellor, Researcher for UNSW, and an Australian Federation Fellow. He has served as an Associate Editor for the IEEE Transactions on Automatic Control Systems and Control Letters, Automatica, IEEE Transactions on Control System Technology, and SIAM journals on Control and Optimization. Currently, he is an editor for Automatica. He is a fellow of IFAC, the IEEE, and the Australian Academy of Science. His main research interests are in robust control theory, quantum control theory, and stochastic control theory. We welcome you, sir, for enlightening us with your research. Over to you, sir.
Okay, thank you. So I'll share my screen. Okay, so hopefully everyone can see the screen now. In this talk, what I want to talk about is the analysis and synthesis of negative imaginary feedback control systems. Okay. So this is an area of research I've been doing for quite a long time, and the motivation for it is the vibration control in flexible structures, such as might arise in a variety of aerospace applications, such as large space structures, flexible dynamics in air vehicles, also in nanotechnology applications, such as in nanopositioning, control of atomic force microscopes, and control of optical interferometric sensing systems. So the particular problem that occurs in such vibration control problems for flexible structures is that there may be unmodeled dynamics, which are often called spillover dynamics, which may severely degrade the control system performance or even lead to instability. Also, there may be significant uncertainties in things like the mode frequencies and damping that can also lead to similar problems in control system performance. So here's one of the motivating examples, the atomic force microscope, which operates at a microscale and has a flexible structure consisting of a cantilever as well as a piezoelectric tube actuator, which does the actuation and sensing in this device. So the idea of this negative imaginary systems theory is that it aims to provide a general systems theory framework for robust control of such flexible structures. So it allows for the design of controllers to increase the damping of the modes of a flexible structure. The controllers are also robust against uncertainty in modal frequencies as well as unmodeled spillover dynamics. Also, it is useful in control of flexible structures involving the use of piezoelectric actuators and sensors. So here's a simple laboratory experiment involving a flexible structure and some piezoelectric actuators and sensors. So in modeling such a flexible structure, then often what we use is some sort of an infinite series like this to represent the transfer function of the structure, which contains an infinite number of modes, which are described in terms of this infinite sum. So if we take the what's called the Hermitian imaginary part of such a transfer function matrix, then what we'll get is a quantity like this, which is negative semi-definite for all frequencies. And in the scalar case, when we've just got a single input, single output flexible structure, that just means that the imaginary part is negative over all frequencies. So because of that, we call such a transfer function negative imaginary. And it turns out that any flexible structure with co-located force actuators and position sensors will have this negative imaginary property for its transfer function matrix. So the formal definition of this negative imaginary idea was given quite a long time ago by myself and some of my colleagues. And transfer function matrix is negative imaginary if it has no poles at the origin or in the strict right half plane, that this negative imaginary quantity, the negative of it is greater than or equal to 0 over all frequencies except pole frequencies, and then if we do have a pole on the imaginary axis, then it needs to be a simple pole with a residue matrix which is positive, semi-definite and Hermitian. And some generalizations of this definition have been made in the subsequent time. The restriction of no poles at the origin has been removed with some slightly more complicated definition, and also in more recent years there have been some extensions to nonlinear systems, but we'll be concentrating on the linear case here. So in the single input, single output case, then this negative imaginary property can be thought of in terms of the phase of the transfer function, and simply that the phase has to be in the interval from minus 180 degrees to 0 at all frequencies. So this might be a typical phase Bode plot of a negative imaginary transfer function. The phase lag is always between 0 and 180 degrees. Another way of thinking about it is in terms of the Nyquist plot for a single input, single output system. Then we might have a like Nyquist plot for just positive frequencies, and that Nyquist plot has to live in the bottom half or the negative imaginary half of the complex plane. Hence the name negative imaginary system. So also in conjunction with this definition of negative imaginary systems, there's a strict version of it called a strictly negative imaginary system, which requires that now we don't allow for any poles on the imaginary axis at all. So it's a stable system, and also this frequency domain property about the imaginary part has to be strictly negative. So one of the early results in this area was a result to connect this frequency domain property to a state space model, and this is called the negative imaginary lemma. It's in some ways very analogous to the positive real lemma. In fact, a lot of the theory for negative imaginary systems is similar to the theory for positive real systems or passivity, but with a slight twist in that now we're looking at negative imaginary rather than positive real. In any case, now we've got a state space model for our transfer function. X dot equals AX plus BU, Y equals CX plus DU, and the property that this state space model has to have for the corresponding transfer function matrix to be negative imaginary is, first of all, A has to have no unstable eigenvalues or at the origin. The D matrix needs to be symmetric, and there has to exist a positive definite solution Y to the following linear matrix inequalities. So to illustrate this negative imaginary lemma, we consider a transfer function, this M of S here, and if we do a Nyquist plot of that transfer function, what we'll see is the imaginary part is always negative for positive frequencies, and but what we also see is that there actually is one frequency which gives zero imaginary parts, so it's not strictly negative imaginary. So this is the Nyquist plot corresponding to this transfer function, which we can see has, for positive frequencies, the Nyquist plot is always below the real axis, so the imaginary part is always negative. But there is one frequency at omega equals 1 radian per second, which gives us the Nyquist plot just touches the real axis, so it's not strictly negative imaginary. So we want to illustrate this negative imaginary lemma applied to this example. So we find a state space realization of that example, and then look at this linear matrix inequality here and try and solve that for the unknown matrix Y. And using some standard LMI software, we find a solution which is positive definite, and therefore conclude from this again that this transfer function is negative imaginary. So the main use of negative imaginary systems theory is actually to guarantee robust stability. And in particular, the main result on negative imaginary systems theory is a result that says if we have the positive feedback of an NI system, a negative imaginary system, and an SNI system, a strictly negative imaginary system, and then that the corresponding closed loop system will be stable if and only if the loop gain transfer function at zero frequency is strictly less than 1. So this is very similar to a corresponding passivity result, except that we've got this additional requirement now that the DC loop gain has to be strictly less than 1. So this general stability results provide some theoretical justification for some robustness properties of some earlier methods which were used in the control of flexible structures, such as positive position control and integral resonant control. It turns out those control methods all involved a negative imaginary controller, and so would be captured by this result. So this is the positive feedback interconnection we're talking about. So say M of S is negative imaginary, N of S is strictly negative imaginary, then provided the loop gain is strictly less than 1 at zero frequency, the closed loop system is guaranteed to be stable. And that gives us robustness because, say, the plant represented by M of S, doesn't matter how it changes as long as it keeps this negative imaginary property, which we can guarantee just by the physics of having co-located force actuators and position sensors, then we guarantee to get stability as long as the DC gain condition is not violated. So the proof of that theorem, the negative imaginary theorem, involves using that negative imaginary lemma and to construct a Lyapunov function for the closed-loop system. So we won't go into the details of that here, but instead we'll look at how we could have a simple proof in the single input, single output case based on the Nyquist criterion. So, and this gives us a simple interpretation about why this theorem holds. So because we're using positive feedback, then when we use the Nyquist criterion, the critical point that we look at is the point S equals 1 plus J0. So we know that negative imaginary systems have a phase lag between 0 and 180 degrees, and an SNI system will have a phase lag which is strictly in that interval. So that means that when we form the cascade of the NI system and the SNI system, the corresponding loop gain transfer function will have a phase lag which is in the strict interval between 0 and 360 degrees. And so what that means is the Nyquist plot excludes the positive real axis for positive frequencies. So diagrammatically, we could look at it like this. So we also assume that at infinite frequency, the loop gain goes to 0. The loop gain is strictly proper. So at infinite frequency, we end up with the origin. At positive frequencies, our loop gain phase is between 0 and 360 degrees. So it's never 0. And so that means it can't touch the positive real axis except at 0 frequency. And that's why 0 frequency is important. So provided we have this assumption that at 0 frequency, i.e. the DC loop gain is strictly less than 1, then we won't be able to encircle the critical point, and therefore, according to the Nyquist criterion, our overall system will be stable. So formally, this result then generalizes to the multi-input, multi-output case, when we've got an NI transfer function matrix and an SNI transfer function matrix. We've got this assumption that at infinite frequency, the loop gain is 0, and then the result is that the positive feedback interconnection that we've been looking at will be stable if and only if the maximum eigenvalue, because now this is a matrix, is strict of the loop gain at 0 frequency is strictly less than 1. So in the general case, the proof uses the negative imaginary lemma, and in the special case, the single input, single output case, those Nyquist arguments that I just gave give you the result. So let's look at an example of this. So suppose we've got the same transfer function as we had before as n of s, and we've got m of s as just a first order lag, and we look at the Nyquist plot of the corresponding loop gain transfer function, product of these two transfer functions, and we can see that now the only time that phase is 0 is at 0 frequency and infinite frequency, and also the DC gain is strictly less than 1, so we guarantee closed loop stability. What I want to move on to now is looking at some ideas about how we might synthesize controllers using this negative imaginary systems theory. And the idea we'll look at is to construct a state feedback controller in order to try and make a system negative imaginary. And the first approach we'll look at is an LMI approach. So the idea is that we might have some nominal plant which is not negative imaginary. It's connected to some uncertainty delta of S, which is negative imaginary. It represents, say, the transfer function of a flexible structure. Then we want to apply state feedback to that nominal plant in order to make the nominal closed loop transfer function negative imaginary, and then provided the uncertainty is stable and strictly negative imaginary, we can guarantee closed loop stability. So here we're assuming we've got full state feedback, and that enables us to get a quite straightforward solution using LMIs. If we don't have full state feedback, if we have output feedback, it is possible to solve this problem, but things become more complicated, so we won't go into that. Okay, so this is our nominal plan. It's got a uncertainty input, uncertainty delta enters in this channel corresponding to matrix B1. We've got our control enters into the system via the matrix B2, and the input to the uncertainty comes from this output Z1. So the idea is we want to find a state feedback control, or U equals Kx, to try and make the closed loop system negative imaginary. So we've got this corresponding closed loop transfer function. We want that to be negative imaginary. And in this LMI solution, we get a sufficient condition in terms of these LMIs and the corresponding solutions if we can find parameters epsilon and alpha sufficiently small such that these LMIs have a solution, then from those solutions we can construct the corresponding controller which robustly stabilizes our uncertain system. So to illustrate this, let's look at an example. Here's our nominal system. It's made up of various components. They might correspond to, say, actuators and sensor electronics, which we have some model for. But included in this is a flexible structure, which we haven't got an exact model for, but we know is got co-located force actuators and position sensors, and so therefore would be negative imaginary, or strictly negative imaginary. So the force applied to the structure is labelled X2, and the deflection of the structure is labelled Y. So we want to construct a state feedback controller, as we said before, and we'll replace the transfer function f of s by a constant gain of 1, and this uncertain transfer function delta of s, which will also be strictly negative imaginary. So essentially what we're assuming here is we're looking at the case when the flexible structure is not flexible, it just has a gain of 1, and then all of the flexibility is assumed to be uncertainty and incorporated in the transfer function delta of s. So rewriting our block diagram, we'd have the following situation, and then we want to apply state feedback to the nominal system here to guarantee robust stability in the face of this flexible uncertainty. So the first thing we do is a state space model of the nominal system, which we get like this, and then we've got the A, B1, B2, and C matrices in our standard approach. We have to choose some parameters as small values. We'll just choose those in this way. Then we apply the MATLAB LMI toolbox to solve the corresponding LMIs, and then we sub that in to find the corresponding state feedback controller, and then according to the theory, that closed loop transfer function should be negative imaginary. So we can verify that again by doing a body plot of that closed loop transfer function, and what we see is that the phase of the body plot is between 0 and 180 degrees. So we've got the negative imaginary property, and also notice the DC gain is a bit less than 0 dB, and so that's also going to enable us to guarantee the DC gain property. So we've got that phase property, DC gain is less than unity, so provided our uncertainty transfer function also has a DC gain strictly less than 1, then we'll get the negative imaginary theorem will enable us to guarantee robust stability. So I'll just finish up with another method of solving the same problem. And this method uses, again, we're solving the state feedback NI problem, but this time, rather than using an LMI, we're going to use a method which involves solving Lyapunov equations, which might be quite a bit easier numerically than the LMI method. So we've got a similar setup with a nominal system. We've got some uncertainty. So one drawback of this method is that we need the nominal system to satisfy some extra assumptions so that we can solve it in terms of this Lyapunov equation method. And these assumptions essentially amount to a requirement that the nominal system is relative degree 1. So normally negative imaginary systems can be relative degree 1 or relative degree 2, but in this method we're only allowing relative degree 1. But an advantage of this method, apart from the numerical advantage, is that we can not only stabilize the system, but we can also give a guaranteed degree of nominal stability for the closed-loop system. So the idea is we first specify a parameter epsilon, which is going to specify how much nominal stability we want, where the poles of the nominal system are going to be, how much we damp our resonant modes. Then we apply a Schur decomposition to this transfer function, which will then give us a decomposition like this. And this is essentially decomposing the zeros of our system into unstable and stable zeros. And we only worry about the unstable zeros. We also do a corresponding transformation to the rest of the system. And then the result is that we solve a pair of Lyapunov equations which only relate to these unstable systems. So the subsystem corresponds to the unstable zeros. We solve these two Lyapunov equations, and then provided the difference between the solutions between these two is positive, t is strictly greater than s, then we can solve the corresponding problem. And this is the formula we have for the state feedback gain matrix, and turns out that this matrix PF is going to be the matrix that occurs in the negative imaginary lemma. So this method is actually a necessary and sufficient condition, provided we satisfy the initial assumptions. It also allows for a degree of stability to be specified. It has the advantage that the disadvantage that we require these extra assumptions, which restricts to relative degree 1 systems. Okay, so that's all that I want to say today. So in conclusion, we've considered a class of systems termed negative imaginary or NI systems. We've shown that the consideration of these systems leads us to some robust stability analysis results about the feedback interconnection between NI systems and strictly NI systems relating to the DC loop gain. We've shown that this can provide analysis for analysis of robust stability of lightly damped flexible structures. And also it captures some of the early sort of more practical approaches that were used by engineers in the 80s in solving these problems. And it's quite similar and complementary to the passivity approaches. We've also considered the state feedback synthesis results, which, if we've got state feedback, enable us to systematically design controllers that can exploit this theorem. We've got two methods, the LMI method, which works, which is very general, but only as a sufficient condition, and also may involve difficult LMIs to solve if we've got high order models. And the second method involves Lyapunov equations, which may be easier to solve but it requires this assumption that restricts to relative degree 1 systems. Okay, so I think that's all that I've got to say. So I'll stop there and ask if there are any questions.
Okay, so thank you, Dr. Peterson, for your very informative talk. I'm Dr. Tiwari, with whom you were in contact from last 1.5 months. From India, right? So it was.
Yes. Yeah, nice to talk to you.
Yes. So this was very informative talks, and one of the question that comes in my mind that there is a requirement of perfectly square matrix for applying this negative imaginary feedback system. So
yes.
Is this the compulsory that if we don't have the perfectly square matrix, then can we not go for this application?
So I guess the original motivation came from the fact that we have, when the requirement that we have, if we have co-located sensors and actuators, so you might think, well, if we have more sensors than what we need to have co-located sensors and actuators, then maybe it should still work. I think there have been some researchers have been looking at this. If you've got more sensors, then maybe you can apply some kind of a scaling of those sensor outputs to reduce the number of measurements to equal to the number of actuators in such a way that you guarantee the negative imaginary property. So that's one way people have looked at doing it, is essentially if you have more sensors, you'd think that would be a good thing, and then you work out how to combine those sensor outputs in such a way to make the overall system square and negative imaginary.
And there are some cases where we have a very highly nonlinear system, which we cannot linearize. So in that case, what is the solution for this?
Well, recently we've been looking at trying to extend this theory to the case of nonlinear systems. And so we do have some results with some of my students published fairly recently about how you can do this. And it's in some ways very similar to what happens in the passivity theory. So you have to find a storage function which has certain properties. So it's related to this negative imaginary lemma. Essentially, the negative imaginary lemma finds the storage function for you. But in the nonlinear case, there's not a systematic way of finding that storage function. You have to use your physical intuition about the nonlinear system. So often, a good choice for a storage function might be, say, the energy in the system. If you've got a mechanical system, then you might just add up all the kinetic and potential energy in your mechanical system, and that might be a good choice of the storage function to prove the system is actually negative imaginary. So I guess it's similar to a lot of results on nonlinear systems. It's possible to do it, but it requires more work in finding a good Lyapunov function or finding a good storage function is something that you can't do systematically. You have to just do on a case-by-case basis.
Okay, so thank you very much for taking the questions, and your talk was very informative, and that has given us an idea how to move forward into a new research direction, because till now we were talking about the negative feedback only, and you brought a new theory itself, that you were the original thinker about this theory. I have seen it, your papers.
Yes.
So that's great, and we welcome you and thankful that you have joined this session for delivering your talk. Thank you. Thank you very much.
Okay, thank you very much for inviting me. And if you don't mind, I'll stop now because I'm in Los Angeles and it's getting quite late. So thanks again for inviting me, and your conference is very successful.
Okay, sir. Thank you.
Yeah, bye.
Thank you very much.
Thank you so much, sir, for imparting your wisdom in this session. As the next presenter has yet to join, we will take a few minutes break before the next presenter has joined. I am sorry for the inconvenience that has been caused. Uh, Now, on to one second speaker. Dr. Ankur Balian, sir, is presently working as Senior Research Scientist in Fuel Cell Cutting Edge Research Center Technology Research Association, NESRAD, Kofu Yamanashi, Japan. At present, he is working on cutting edge high throughput analysis techniques and next generation scientific analytical platform development for fuel cell. The analytical platform is powered by machine learning analytics for high-end analysis such as quantum beam analysis. His area of interest are nanomaterials like carbon nanotubes, carbon nanowalls, cellulose nanofibers, carbon fiber reinforced plastics, etc. He is also interested in device fabrication and product development of lithium air batteries, lithium oxygen batteries, and lithium ion batteries, fuel cell, and smart, miniaturized, portable, and non destructive spectroscopy instruments. He has also worked on artificial intelligence based autonomous materials research using scientific instruments and quantitative and qualitative data analysis using machine learning techniques. He has more than 14 years of industry experience in fabrication, categorization, and analysis of wide range of materials and devices. He also holds 4 patents and has published dozens of research papers in peer-reviewed journals and holds expertise in development and implementation of large software framework for analytical and business process solutions. Kindly enlighten us, sir, with your wisdom. Over to you, sir.
Thank you very much for the introduction. So, first of all, I would like to clarify, are you able to hear us? Hear me?
Pardon, sir?
So, can you hear me?
Yes, sir, you're audible.
Okay, how about my slide? Are you able to see my slides?
Yes, sir, your slide is also visible, sir.
Okay, great. So, thank you very much for the introduction. And I would like to, before I start my presentation, I would like to thank Dr. Haminder Singh and Dr. P.M. Tiwari, and of course, the MEG University basically for the invitation and organizing this conference. I hope this will be very helpful for the students. So welcome to the presentation. I'll be speaking on characterization techniques, cutting edge instrumentation, and role of machine learning for sustainable hydrogen society. So since we are creating an ecosystem for the development of next generation fuel cell, at present I belong to the XCubic, which is basically a government facility for the fuel cell development. So let me take you to the presentation. So what is, the question comes is, what is sustainable hydrogen society? So sustainable hydrogen society is basically primarily where the hydrogen is the primary energy carrier. And when we talk about this, we talk about 3 important aspects of it. One is the production, distribution, and utilization. That means we generate hydrogen, or we produce hydrogen from the green sources, then we distribute it in a green manner, and then we use it in terms of hydrogen. And then hydrogen, as you can see from the slides, let me take you to this pointer. I think that will be grateful. So we generate basically the clean energy, and then we transport that hydrogen, and hydrogen can be used various ways. Of course, you can power your, much of the familiar is like your car and buses and transportation and so forth. But of course, you can transfer that hydrogen grid to the power grid also, and then it's like, the hydrogen and the EV combination started to dominate. So we need to understand few facts. If you really see this image, the global fuel consumption in the year 2021, you will find that almost 80% of the fuel consumption coming from the light, medium, and heavy duty vehicles actually. And since we are more familiar with the cars, So only 15% contribution among this 75% basically is coming from the passenger cars, like the cars that we use for transport. That means almost 60% is not from the passenger car, but from the light vehicle, such as small pickup trucks or the heavy duty trucks and so forth. So that means 50% passenger cars can maybe possibly converted into the electrical vehicle, but 60% market possibly in the future is going to be dominated by the fuel cell. Coming to this side, where we have the global commercial vehicle market, if you really see, many hypes are still there, but you can see that still almost 80% of this market is basically still powered by the diesel engine. And if you really see the fuel type, many people believe that there have been radical changes in terms of the EVs, but there's only 5%, or maybe just not even 5, maybe 3%. The present vehicle basically are the EV vehicles. So you can imagine that we had to basically go a long way before we go to the sustainable society. So many times actually this kind of question comes up. So I don't want to debate which is better, like the electrical vehicle is better or the fuel cell is better, or who will win the race. But frankly speaking, this graph speaks a lot. So this yellow one is like EV car actually, and this is the expense, and the blue one is the fuel cell. So if I explain this in a layman term, it's like if you travel almost, let's say, 200 kilometers per day, it's better to have the EV that you buy a car. But let's say if you travel, let's say, 1,000 kilometers, the expense for the EV is going to be almost 3 times in comparison to fuel cells. So if it is good if you travel more than 200 kilometers, we should go for the fuel cells. Fuel cell applications, like we see that 60% of the market, as in the previous slide, we will have the large commercial trucks, small commercial trucks, and taxi fleets. In the near future, you will see the radical changes in terms of the cars. No one possibly would want to own the car. Maybe there will be taxi fleets, and those taxi fleets will be powered by the fuel cell alone. There will be less chances for the EV to be there. So what is a fuel cell? This is for those people who are not familiar with the fuel cell. So it's much like your conventional battery. Of course, I mean, this is just an analogy. So what happens is you have the hydrogen coming from this side and the oxygen coming from this side. You have an anode, you have a cathode, and there's a separator, like an ordinary battery or lithium-ion batteries. What happens is basically this hydrogen at this particular anode, which has a catalyst, it makes this ionize. So the electron goes into the circuit outside, which you can use in terms of load, or you can withdraw some current from this. And then hydrogen basically, which has a proton, and this is a membrane in between. So the membrane allows the proton to move in. Go across this membrane and reach here at the cathode. And then the oxygen and the hydrogen proton basically and the electrons join together to form an water basically, which is the exhaust. So it's much like a clean fuel we have. So if you look into what constitute a fuel cell, you have the anode and cathode. And of course, the fuel is hydrogen and oxygen. And in anode, you have the platinum and carbon, and cathode, you have the platinum and carbon. Of course, there are variety of catalysts exist, but here we use platinum as a catalyst and cathode. But people are not bothered about much on this anode. Most of the research is happening in this cathode platinum. We'll see in the next slide. But if you really see that this kind of particular one cell only gives us 0.7 volt of potential, that means to have some kind of practical application, we have to have like 50 or 60 or 70 cells, we say the fuel stack. Since it's like what's in a layman term, if you really see a single unit of fuel cell, this is how it looks like. You have the hydrogen coming from this end and the oxygen maybe from this end. Then you have basically this, you see that the MEA, we say the membrane electrode assembly. This particular portion is where basically you have cathode. The other side is you have anode, and then you have the membrane. And this black one that you see is basically the gas diffusion layer. This gas diffusion layer does nothing, when the hydrogen comes inside, this gas channel basically distribute evenly. And then just to maintain the pressure, basically this gas diffusion layer is there so that, the hydrogen gas equally can be distributed on this anode and from this side to the cathode. So as let's spoken, a single unit cell is only gives you 0.7 volt. So for a meaningful application, we have to have like 50 to 70 stacks. Once the stacks is like, the each one is like one cell. So there may be 50 or 70, but since the number of cell increases, we need to think of the thermal management also at that particular point of time. As I told you already that since the anode, there's nothing much, of course, you can improve, but you can see the weightage in terms of the cathode and anode is here is, the reaction pathways, this is the most important. Many things are happening in cathode. So people would like to, explore cathode rather than much on, invest more time in cathode than anode. Of course, one can investigate and spend their time in terms of anodes. So looking to the key research areas, one is the catalyst. We would like to do the catalyst development, which is particularly for the cathode only. People are looking on the innovative fuel cell design. Can you improve this fuel cell in such a way so the weight reduces and it started to give you more energy density? People are also looking to the membrane electrode assembly, which is like, I think I'll explain you in the next slide as well. So these three are the main key areas that people are focusing. And good thing about the fuel cell is that if you see that we have the platinum coming up here. Since the platinum is the only catalyst that we are using, so the geopolitical significance is, it doesn't have much exposure to the country-specific restrictions. Like to EVs. If you look at the EVs, lithium reserves are mainly controlled by China. Or cobalt reserves and so forth. So I don't know basically how far EV can be sustainable if we have the geopolitical scenario continues. So what is essential for the fuel cell is we need to find out, because many reactions are happening, so we wanted to explore the reaction pathways. I would take some time to explain this system, which is essential. So what happens is the hydrogen comes from this end, and since this is anode and this is cathode, and this layer basically is a membrane which allows the proton to pass through it, and it doesn't allow basically electron to pass through it. So what happens is the hydrogen comes in, and this GDL, which we say gas diffusion layer, which is nothing but the fiber of carbon, equally distribute that hydrogen so that the equally it can be get exposed to it. And then you have PTFE, which is like, the hydrophobic layer of carbon. So what we do is we paint this hydrophobic so that, the water or the moisture that is inside the cell does not go out or doesn't create a short circuit and so forth. So essentially, if you see this pink one, this black round red dots are like carbon. They are good conductor for the electrons, and the blue one are good. This is ionomer. It's a good conductor for the proton. And of course, so what happens is when the hydrogen comes in, there is a catalyst which is platinum. Platinum basically, the hydrogen breakdown in terms of the hydrogen ion, and electron goes basically out to the circuit. And then proton basically, since this blue one path is a conductive path, so you need ionomer for this conductivity to be there, and of course the water also can be a conductor. So then it comes here, and the proton basically passes to the other end. From the other end, you have the oxygen coming, and of course this electron. So this electron, oxygen, and this hydrogen ion join together at this particular catalyst, which is again the platinum. So which we call this as a triple phase boundary, where you have the catalyst, ionomer, and carbon support. If any one of these is not there, the reaction cannot be completed. And even if you have catalyst, it's not contributing to the system at all. So once that reaction happens, the hydrogen, the proton and the oxygen basically, and the electron combine together and produces HO2, which is water, and basically the water comes out. And that's what I said, the focus of next generation batteries, the fuel cell is in terms of the catalyst development, which is platinum. Many people are working on this. So this three-phase system is a very, very essential, and many people are researching at the moment. So if you look into the IV curve and the power density plot, as you can see that, the slowly as you basically, with the current, slowly started to go down, and down, so forth. And when you plot basically the power density plot, you can see this is the highest here. That means at this particular point, there is of no use, taking the, going to the, this end rather than, the stable region is from here to here. And this is 0.6 and this is 0.8 and 0.7, 0.6. So the average is like 0.7. That's what I said in the earlier slide also. It is like 0.7 volt of potential from a one cell can be taken, and hence that is necessary to have many cell in series so that we can have some practical application. As I already explained in the last section, but it's important here, you see that we have the carbon support so that our electron can move through it because it's conducting. And sometimes the electron support has a small hole, which we say micro, and then you have the major hole, which is we say macro or mesoporous. And the space between these are we say macropores and so forth. So the porosity increases slowly depending on how do you distribute it. But essentially, the important is to look at this particular point of time. As I said, electron is conductive if it is passed through this carbon support. And we need basically the ionomer or the water, which allow basically the proton to get conductive, the proton to move ahead. And this is basically the green color that you see is the catalyst. So, and the oxygen comes here, and oxygen, so you have a triple phase boundary. So these three things are essential. So many people are working to find out what is the best combination for catalyst, ionomer, and carbon support. And many people are focusing on to find the best catalyst actually. How possible for us basically to have this slope not like this, like if it became like something like this. So if it became extremely flat, that means it's going to be something like not 0.7 average, it is going to be around 0.8, and which will almost increase the power density by twice in the same space of fuel cell. So many people, since I already talked that the catalyst is the most essential part of the fuel cell system. So many people are working on this to understand that how the catalytic mechanism started to take place. So to understand the catalytic mechanism, we need the instrumentation or the characterization we need to do. So so one is called the unimodal characterization. Unimodal characterization means one kind of characterization you do, and you try to come up with some kind of hypothesis that okay, this is what is happening. But very recently, people are doing like the multi-modular approach where you have multiple instruments, and from the knowledge coming from all those instruments it gives some meaningful, much better approximation than the unimodal. So that's called multimodal or integrated analysis reason. Since you see that you already saw the fuel cell, so the active component in fuel cell. You have the catalyst, and catalyst is made of atoms, and atoms are again arranged in like the unit cells. In terms of material, if I really talk about, and it has proton, and of course it has the electron or its distribution. And since as you can see that since this catalyst is basically in close proximity to this carbon support. So we need to think of this also. So this can be a few micrometer, a few tens of micrometer, basically. So the interaction length is it's going to be atomic to micro level, or sometimes to meso scale. So that means a single modular approach is not enough. We should include basically to see a very good picture. We should have to have this whole regime included into our characterization. So if you look at if you have the platinum only material and you look into the area specific activity of fuel cell, you find the area specific activity is small. But when you dope basically with some certain element or make this an alloy, So you see that area-specific activity increases. That means there's a lots of scope to find what is the best catalyst or the alternate of the platinum, because platinum results are also limited. So one more aspect of this is you have the particle size also, where basically the catalyties are impacted. If you see from this figure, you can see that we have the particle size here around 2 nanometer. If after 2 nanometer, basically the mass activity started to go down. So that means the ideal size of our catalyst is around 2 nanometer. So So essentially is remember this, what kind of characterization we need. We need characterization which can tell us basically the particle sizes and of course their interaction scale and their various kind of So we need to investigate this kind of sample with some characterizations. And for that actually, I'll skip this for the moment, but I think it's good to go. So what happens is, this is for those people who do not know much about the lattices or the crystal structure. So this is the carbon support. One particular here, this is basically a catalyst. If you zoom out the catalyst, you will see that the catalyst has certain crystal structure. And inside the crystal structure, you have the interatomic distances. So we have seen that the interatomic distances, when it changes, basically contributes to the catalytic activities. That means we need to find a way so that we can know the interatomic distances and the crystal structure. At the same time, if I go back, we need something to tell us basically what particle size is, and of course, basically how the alloy basically influences and its surrounding. So to do so, most of the people use an instrument which are in their lab, but frankly speaking, those instruments are like a toy, because the energy that they generate is not that much, so that you can probe individual atoms or individual crystal and so forth. So you can use them for screening purpose, but if you really wanted to understand some mechanism meaningfully, you have to have some kind of synchrotron radiation. And I'll be speaking not for those people who do not know the synchrotron centers. What happens is it's like the very large ring of an accelerator. Here, what happens is we launch an electron, and then using the magnets, basically we accelerate the electrons in such a way so that the slowly speed of electron goes in terms of the speed of light. And once that happens, basically, once that electron beam passes through the magnets, which we call ondulators, the electron started to radiate energy, and that energy is, you can see in your right hand side. So this is a XR ray. You can generate soft X-ray, or you can generate hard X-ray, and so forth. And the energy of those is really intense. In terms of the radiance, if you measure. So in Japan, we have such kind of various synchrotron centers, but very famous is like Springate, with whom we are working at the moment. So you can see there are almost 40 beamlines. Beamline is like one kind of characterization that you can do. So you can do the diffraction characterization, you can do the spectroscopic characterization or imaging characterization, depending on which beamline do you use. So to understand, as I already mentioned earlier, that actually if you take just one analysis, it's not enough. It's called unimodal analysis. You have to have at least 5, 6, or 10 analysis to see a clear picture, something like the one that you see here. It's an elephant, but the people who touch different parts of it, they feel something different. Let's say this person sees it's a wall because he's looking only this portion. So to understand something in terms of mechanism and to see the reaction pathways, we have to have basically the cutting edge characterization or instrumentation. We call it the integrated analysis. And this is where basically the scope for the students probably is, because this kind of instrumentation does not exist. And sometimes you need to modify it, you need to redesign it. And there are very highly paid professional actually who does that. So in the quantum beam analysis, we do 2 different kind of characterization. One is called spectroscopic, and another one is imaging characterization. Here I'll be talking about the 6 different kind of characterization. 5 primarily. So we have the XRD. Then this is to know basically the crystal structure. Then we have the ZAFs. This is to probe the coordination number. And then we have SOCs to know the thickness. And we have the PDF, which is the total X-ray scattering, basically, to know the beyond 5 nanometer, if any kind of crystal that is, or any kind of systematic arrangement we have. And this is Hawk's XPS, which is basically to know the valence band probing or the kinetic or binding energy probe. And of course, in terms of imaging, we have the nano-CT, where you can scale, you can slice basically the electrode, and then you can see the distribution of water, or you can see the distribution of catalyst or the carbon or ionomer and so forth. So I summarize everything here. We have different options there, but this is primarily for the lattice constants, of course. Other information has been given below, but since because of the time constraint, you can see that we can probe basically the lattice constant with XRD. And we have the ZAFs. We can probe basically the alloying degree. That means we can probe the local structure. And this PDF basically is a counter of ZAFs, because this can only probe up to 5 nanometer. But this can probe beyond 5 nanometer, like 10 nanometer or 20 nanometers. So that means it can locally, it can analyze, but it can really do much kind of tens of nanometer scale. Then you have the SOCs, which is for the self-assembly kind of, we can probe the particle size as well. And then we have this Hawk's XPS to probe basically the electronic state, which is like, the band gap and stuff, if they're contributing, because the D band here contributes a lot in terms of the particle calculating activities. Of course, we should also talk about the imaging. If you see the imaging, there are different kind of imaging, of course, you can do. You can do the STEM imaging using the TEM, or you can have the SEM also to know the 3D structure. But here at the moment, we are looking to the STEM images. So this is one this is the catalyst line basically out there. This is the front view and the back view. If you see the dark STEM mode and the bright STEM mode, you can see that the catalyst is visible. And from this catalyst, you remember that we talked earlier that we need to calculate the particle size. So that's where basically using this image and machine learning, people can calculate the size of individual, and you can plot basically the particle size distribution. And of course, you can see the carbon structure here. To see that what kind of carbon that has, which is not visible in the dark field image. So I'm coming slowly to tell you basically what is essentially important and not many people are doing at the moment. So we have the automated measurement system that we are working at the moment. So to understand this, it's like the autonomous control and you can say instrumentation frozen. So if you really see that we have this, let's say if I want to do a spectroscopic measurement, so this is a conventional system. And that I say that, okay, I want to measure this point, and these points, that they are equally separated. That means, let's say I have to do 700 point measurements. So if you want to do the 700 point measurement, this is how I do. So the light is there, and then you have a grating. Basically, you tilt a grating, and based on the small grating, basically you can have the detector, and detector detects it. And then when you go to the next stage, you tilt again grating, and you get the next position. You tilt again grating, and then you get the next position, and so forth. But what happens is you have to tilt this grating 700 times, basically, to know the position. And the important question is it necessary to have the 700 points? Because in this particular point, there is no information. So it would be better if I measure it sparsely, and if I find much better information. And so that information I can have, that these points are very closely to each other. So for that, we use the machine learning or Bayesian optimization technique. So rather than taking all the discrete measurement, we design a system where the system will take over everything by itself. You tell in the beginning, let's say like this, you say that randomly you measure any 10 points, and then for the next point started to basically the system, Bayesian optimization start to propose, okay, you investigate this point or this point or this point. But the problem is these points are not in sequence, so you cannot, so they are all random. So maybe it can say that, okay, you measure here, and the next point it can say measure here. So this grading has to be, the randomly oriented. So at the moment, the control system or the software are not designed in such a way so that they can take the Bayesian optimization can be faster. Rather, that we have to change up to the whole way, which takes time. So there's lots of opportunity for the engineers in this particular field, where we say the measurement informatics. So as you see slowly, so this is a variance actually, the blue color you see, when we add more point, and remember this, these all measurements are being done by computer. I mean, the robot itself, we are not doing anything, but we are not fitting any system, or we are not defining any, you measure on this point or this point. The system slowly add point by themselves, and then further it measure, like this is 60 point, and you can see the uncertainty goes down. And then you have 94 point, you can see that we have still little bits of uncertainty. And after 116 measurement, basically we have captured the entire spectrum. We don't need, even if you go beyond 16, like 178 points, basically there's nothing here to be more captured than this. That means the 700 measurement point was redundant. That means if you can have this in with 100, that would be great. And remember, you have not done anything. This system is intelligent enough to decide by itself where it is going to drop. And this happens so as I said, that there are lots of opportunity for the system engineers to redesign in terms of the smart instrument, smart control softwares, and autonomous machine learning measurements actually. So to those people who do not know the little bit of Bayesian optimization, I think I would advise the students to go through that and learn a little bit of it. But it is something like this. You see that it's using the Bayesian optimization, you can coming from this, measuring this particular plot has basically an objective function, and we call this a black box. So this is a black box, and we wanted to map that black box. We want to learn that how that function is actually. So we say that it has an acquisition function counter to that, and let's say it automatically gives you the position which is highest. That means it says, I have the less confidence at this particular point. If you measure here, my confidence will improve. And once it does basically measure there, then basically this curve changes. And that says, this is the highest point. My confidence at this particular point is low. If you measure at this particular point of time, basically my confidence will improve. And this curve slowly, that means the black box basically started to take the shape of the instrument function and so forth. So this is called autonomous measurement system. This is the future where basically people are working. Since we have the measurement system, of course, we need to have the analytical system as well. So you have to have the database, because we are not going to do any unimodal analysis. We're going to do multimodal analysis. And at the same time, this data comes in, you need to have expertise, the domain knowledge people. Domain knowledge is the people actually who are good in terms of, let's say, fuel cell. They will make a dictionary, and based on the dictionary and the data, we will design basically an application in terms of, so that, the analysis can happen autonomously. And after the analysis, the report can be shared, or the model that you have made during the machine learning can be shared with your colleague or somebody else, so that the efforts can be minimized. So what we are doing at the moment is, it's called integrated analysis. So you have the energy source. So earlier we were doing this, this beam, this instrument was in a different beamline, but now we are going to, we are making basically a new beamline where all this kind of characterization related to the fuel cell can happen simultaneously. That means you don't need to move the sample. Because earlier when you measure, basically the sample is here, but when you measure from the another beamline, the sample position shifted. That means in a way that the sample is the same, but you have missed basically the position. So the spatial information is lost. However, when you have the integrated analysis, so you need system engineer to design all this together, you see, because this is technically challenging, and the system engineer or control engineers. So what happens is, from the data that you collect, and then you put the data set together, send it to the machine learning model, you train a model, and for that you need the workstation, that means GPUs, which are computationally enough to take the lots of data, and then you can visualize that data, or you can make that model and share it on the cloud and so forth for further analysis, to autonomously analyze it. So we are making this infrastructure, of course, this infrastructure where the data set goes into the databases, and then we have the machine learning platform that we are building at the moment. So where autonomous machine learning model will be analyze the system as soon as you are measuring. That means measurement hasn't happened. I mean, you started the measurement, but the model started to give you clue that this is how either you should measure or this is what basically the answer is possibly coming to be, so that you can shift the position in real time. So I will tell you one more. For the analysis, what we need is we need the data collection, then data pre-processing for individual technique, and then we need the data analysis and data visualization. So one of the use case I would like to introduce to that is that I design a system which is like cosmic noise removal from the Raman spectra. So what happens is that you have the Raman spectra, and you know that we have the cosmic noise. I mean, the cosmic wave, when they pass through the Earth atmosphere, immediately they give basically this kind of spike, which is a kind of cosmic noise into the system. So this is the cosmic freeze Raman spectrum. This is the cosmic noise Raman spectrum. And if you measure like this, thousands of them, and you see that this has a map, mask. So there is no noise, so that means mask is 0. Then you have basically noise which is there. So it says that this has a mask, something like my video that you see as I turn my head. So the mask is basically, so there is a mask being designed by the machine learning, so that, so wherever I turn my head, the mask is generating basically accordingly. So very similar to this system, but this system was like this, that when I was measuring the data, just to measure, let's say 2,500 Raman spectrums, it used to take me around, let's say 3 days and so forth. And that data was not collected itself. But at the moment, we are measuring the data and simultaneously correcting the data, so that we are doing the background and noise correction in the real time. So we can do this in real time. Maybe if you have even 1 million spectrum, hardly it will take 2-3 minutes basically to remove that noise and stuff. So this kind of use case I would like to introduce. So I come to the conclusion where I said already that we need development of the next generation fuel cell ecosystem required following things. One is that you need to find out the bottleneck into the system, which is the bottleneck of individual system, and you need to fix that. That means digitize that system. Focus on the high throughput experimentation. Then we need to design and develop cutting edge instruments and AI enabled data acquisition techniques we need to go for. Of course, the autonomous characterization and AI powered measurement analysis. And it requires basically the capital investment for the human resource, computing infrastructure, advanced instrumentation, and AI. So with this, I thank the following, the NIDO, XC-Cubic, MIT University, and I have a small announcement. We have basically an opening, few openings in our group. Any individual who would like to work with the measurement informatics or autonomous system, they can reach to us. With this, I rest my presentation.
Thank you, Dr. Balyan. It was wonderful presentations, and a lot of things about hydrogen used in fuel cell has been shown by you in the slides, and that is going to be beneficial for the students as well as faculty. And we can go for a direction in this direction for further research. Hydrogen is a clean source of energy for zero carbon, of course, but there are challenges of extraction and then the cost and storage as well. So I think the government has to take some initiative. There should be some willpower by the government to use it as a fuel. So it depends upon the government how they use it. So it was a wonderful talk, sir. Thank you, sir.
Thank you, sir. That was such an insightful talk for all of us. I would now the questions. Lastly, let us introduce the final speaker for today, Mr. M. Zafar. He is heading a team of application engineer, and his main focus is to train customers on MathWork platform on their required applications. Mr. Zafar brings with him around 17 plus years of experience in system design for signal processing and image processing, and is currently working on AI and data science applications. Prior to joining, he worked in capacities such as Central Head for Training Institute of MATLAB, where various courses related to signal processing, communication, and image processing is organized. He also helped students to develop projects related to face recognition and watermarking technologies in its implementation as user interface or incorporate with hardware to integrate real world scenarios. He holds a master's degree in electronics and communication from UIET Kanpur. Please join me in welcoming Mr. M. Zafar to the stage. Sir, the stage is all yours. Hello.
Okay. Good morning to all of you. I hope I am perfectly audible to back. Okay. Thanks for the nice introduction. And my talk is related to electrification, AI, and future of engineering education. Okay. So what we have did, we have taken whatever the say recent trends are there. Like electrification is the biggest trend. Then robotics is there. Autonomous systems are there. In autonomous systems, we can say that AI is there. And furthermore, like 5G, IoT. So these are the recent trends are there. So what we have did, we have taken couple of the trends and tried to incorporate with system thinking. Because of most of the time in engineering education, that system thinking is going to use. So we will see in my talk that how we can incorporate and what kind of features are available within MATLAB so that we can utilize those things to enhance the system thinking itself. Okay. So as I said that we have taken two major topics. I can't cover up all the topics in this short duration. So I have taken electrification and autonomous system. And then we are going to see that how system thinking will work in classroom itself. So first thing first, that electrification is everywhere. How many of you are agree that electrification is everywhere? Very few people. Rest people are using lamps? No? Might be. Okay. Joke apart. So what is it that we are using reusable energies from fossil fuels or from solar systems? Okay. So like these solar panels are there. So in this solar panels, what we have capability that it can say generate some electricity store and then we can later on use that thing. Similarly on wind turbines or fossil fuels also. Or we have say world's first solar plane or electric vehicles are there. So everywhere electricity is going to use. So that's why I'm saying that electricity is everywhere. And definitely when electricity is going to use to operate all those things, what we require electric motors. Definitely. Like you see that whether it's aeronautical systems, whether it's say industrial robots, medical equipment, or household appliances are there. So everywhere motors are going to use, right? And definitely when motors are going to use, we need to control that also. So for controlling, definitely some kind of embedded controllers are there. So we require electronics also over there so that we can embed some kind of code to control those kind of motors so that it can work according to our need, right? So as I said that electrification is everything and everywhere. Okay. So what we are going to do, we are going to discuss in 3 points on this. Why is it happening? Electrification everywhere, and what challenges in industry facing, and how are engineers overcoming to them. Okay. So let's first discuss why it is happening. So any answers that why it is happening, electrification? Any rough guesses also works. No? To reduce the carbon footprints, right? We are using petrol, diesel, so those kind of fuels definitely say creating some kind of carbon footprints. So to reduce that carbon footprints, as well as that, whatever the demand is increasing according to the population in different countries. So to overcome with that, so these are the two major points: demand as well as that removing the carbon footprints. Okay, so this is why that electrification is happening everywhere. Now, next thing that we are going to talk on that what challenges is industry facing. Okay, so when we say that electrification, so these are the key technologies which are currently in use. Like first one is that battery, power electronics, and motor control. Right? We have discussed this thing earlier also that these things are available in everywhere and everything will be controlled by these things. Now, these are the key technologies, but what are the challenges? When we say that challenges, so like battery modeling or safe operation, that whether battery is working safe or not, aging of the battery. Okay, so we all are using that smartphones, and our smartphones degrading their battery life day to day, right? So we need to work on with that also, so that we can get some kind of optimized solution so that it can work in more efficient way. Then definitely for that, what we require a BMS system development, battery management system. Okay. Next, for power electronics, definitely we require some kind of dynamic solution for this. A digital control need to be designed, a supervisory logic need to be designed, as well as that when we are working on this, we need a rapid prototyping. So whatever we have developed on a motor or a system, we need to say prototype on an ECU so that it can control that motor itself. So in motor control, definitely we require some kind of sensor calibration, parameter estimation, efficient algorithms, and control tuning. So last one is that last one and second last in motor control is the most usable things. Parameter estimation, that what kind of parameters we set for a motor so that it can work in very efficient way, as well as that whatever the controller we are designing, how we can auto tune that thing. So these are the major things are there. Okay. So these are challenges are there which industry is facing. Now, how we overcome with this? Okay, so I have one short video. So it doesn't have any audio. I will say speak over on that. What is this? So basically, Lightyear One is a company which has built, not a company, it's startup. Sorry. So startup. Yeah. So they have built world first solar powered car, which run in a single charge somewhere around 450 miles. Okay, and they go through with the MathWorks student competition, and MathWorks is supporting with their startup program with this. So they have built up such kind of say a car which is working properly as a by solar power itself, a completely solar driven car itself. So as I said that it's included in MathWorks startup program. So MathWorks has a startup program. So if anyone from MET is working on some kind of startups, please discuss with us. We can help out you in those kind of cases also. Okay, so we are discussing on the challenges. So because of the time, we can't discuss everything today itself. But what we are going to do, we are going to talk on batteries right now, which is again a biggest say challenge in industry. So when we say that we are going to model lithium ion battery cells, so first thing that will come up in this, that how it is going to charge and discharge. So a typical current and voltage graph of lithium ion battery has been displayed in this place. Okay, so it looked like this kind of thing. Okay, that how your electronic circuitry will be displayed, or you are building on a hardware or on a software itself. Okay, so when we say that how it is charging and discharging, so definitely it has a series resistance which is going to work on that instantaneous response. Then we have a parallel resistance and capacitance which is going to work for exponential relaxation, and in the end that a voltage say power source is required which is going to work for open circuit say potentials, right? So how we are going to use with MATLAB this thing. So this is my circuitry. It's look like that. We have used in that some kind of resistance, capacitance, a load is there, a power source is there. So how we build up this thing in Simulink? So Simulink is a platform for model-based design environment where what we have a proper library available for different components. So you can use these components, which could be from electronic components, let's say active or passive kind of components, or a single phase or three phase kind of say components are available for electrical modeling itself. So by using these kind of libraries, what we could do, we can build up such kind of say could you please remove this? Yeah, thank you. So when we build up those things, what we could do, we can simply say, can you click on that because of it's not, yeah. Yeah, so we can run and we can get that what kind of responses are coming from that circuitry. So this is a quite simple one, that we have some components available, we can use these components and we can develop such kind of things. But we are discussing about a battery management system as complete solution. Okay, so what we could do, we can use a complete lithium ion battery system to build up such kind of models. So we have products available as SimScape battery, which will allow you to design a complete battery pack, which you can say first simulate and then later on use their parameters to actual systems. Now, how those parameters are going to identify? So what we have, so like here you see that I have run out that particular say model, and in that model, when we zoom and say that in this place, in bottom one, that battery voltage. So there are definitely some differences are there with actual as well as that simulated results. So we need to parameterize our model so that we can get very minimum error and get better battery so that it can work according to our need. So for that, what we have these kind of parameters are available. So which can be used for state of charge or temperature of the battery, so that we can fix up these parameters. And with these parameters, we can easily say get desired results. Okay. So what we are going to do, we are going to again use one of the app which is known as, so apps are available. So these apps are ready things which will allow you to perform different operations on your model. So what I need to do, I need to say parameterize or estimate parameters for my model. So what I could do, I can simply go in this app section where a variety of different apps are available. In these apps, what I could do, I can simply go and choose parameter estimator. So in this parameter estimator, what we have options available that we can define multiple sets of data for those say variables which I need to parameterize. And whenever we feel that the error is very minimum, that is the actual parameter which is required to be put in that particular component. Okay. So like you see that it has run multiple iterations on the left hand side of the screen, that estimated parameters has been shown, and it is giving me that kind of results also. Okay. So what we have complete estimated parameters available. Now we can really use these variables within our complete model. Okay. Next, so that model is just for a single cell. When we have multiple cells available, okay, like in this case, what we have 3 cells available, battery cells. How we can say operate this charging and discharging states? So definitely what we need some kind of supervisory logic. So MATLAB and Simulink is providing some kind of say options which is known as state flow. State flow will allow you to define a complete logic. Like here in the middle one, you are able to see there are some logics are there which will show. So when I further execute this, it will show you that how a specific cell is going to charge and discharge. So it will show that all the states to you. and corresponding what are the graphs are there. Like you see, it is highlighting that cell balancing and then which particular cell is charging and discharging accordingly, it is showing me that. So if we want to define such kind of supervisory logic, we can easily define that such kind of supervisory logic within MATLAB and Simulink by using state flow. Okay. Okay. So we have started from a single cell, then multiple cells are there, but or better I can say that multiple lithium-ion batteries. Okay. Now what we need to incorporate into a complete system. And initially I said that we need to tune a controller, we need to rapid prototype that things. So how we can do such kind of things? Like here, when we say that a complete electrical system has been defined in this place, as well as that a complete controller also has been defined in this system. So what we have a complete vehicle dynamics model is there, our engine system is there. So these blocks are readily available within Simulink library under Simscape physical modeling tools. So we can use these blocks and define their parameters. And definitely parameter estimation will work in these kind of cases also. So like right now it's a hybrid kind of vehicle. We can choose out say completely electrical motors also. So we have options available for EV, HEV, both of the kind of things. In engine, different say options are available, so we can choose out accordingly. So what we have this controller. Now this controller is perfectly working on my system simulation, but I want to make sure that this particular controller will work on a ECU also, right? So either I should go and write a complete code for this controller and burn out on a specific controller so that it can work accordingly. Or what I have again a better option. In apps, what I have an embedded coder kind of product. Okay. So embedded coder product will allow you to automatically generate a C or C++ embeddable code for specific device. Okay. So we support variety of different devices, microcontrollers, processors. So you can simply burn out your code on those kind of say processors or microcontrollers so that you can check whether it's working perfectly on those kind of processor or not. So we support SIL, PIL, HIL kind of things. So you can simply use out over there also. So this complete approach is known as model-based design from concept to code. So like first thing what we have seen that we have started from modeling our system and simulating our system. If we go back and see that our RLC circuitry kind of thing. So over there RC circuitry basically. So in that what we have just designed a model, run that simulation, and for a single cell we have first seen, then for multiple cells, and for a complete system. When we are happy with that system, what we could do. So let's say that test early and often. So we can test out our say models in each and every step, that what kind of results are there. If we are not satisfied with that kind of result, we can go back and change parameters, change say motors, or change a complete system also. As well as that, as I said, that automatically generate of the code. So you can generate automatic codes also for that. So why it is needed? Why model-based design is needed? Okay, so how many of you are agree nowadays that products come very early in the market? Like every 6 months a new product is there, or less than that, right? Reason being that people, not only MATLAB, people are using this approach on different softwares. Software could be anything. Okay, so what they are doing, they are using these kind of softwares to say kill the competition in the market. So whoever is the early in the market, they will stay in the market, right? Right. So we have seen a little bit on electrification. Okay. Now, next thing, as I said, that electrification is everything, but alone electrification will not work. If we have only electrification, we can't develop a full-fledged electric vehicle or an autonomous kind of vehicle. So for that, what we need autonomous system, right? And this autonomous system bring along with him AI. Okay, so what we could do, we can incorporate electrification, AI, robotics, multiple things within one system. Okay, so what are autonomous systems? Autonomous systems can be a humanoid robot, a self-driving car, or a drone. So such kind of things will be autonomous system. But whether we are not using electrification in this one, no, we are using batteries, we are using battery management system, and definitely AI also in this, right? So again, we are going to talk on three things. Why is it happening now? What challenges is industry facing, and how are engineers overcoming to them? Okay. So first thing first, that why it is happening now. Pardon? So okay. So is it this thing is not available earlier? When we have graduated, is this thing is not available? Or when sir is graduated, this thing is not available? Okay. Okay. That's fine. I partially agree with you. Reason being, whatever it is using in artificial intelligence, that is corely mathematics, statistical analysis, right? But the thing is that at that moment, we don't have enough data available, right? People are used to store data on papers, right? People doesn't have enough computing power, right? What nowadays we have, right? So yeah, please. Okay. So AI is a very big picture. Okay. In AI, machine learning will be a small part of that. Okay. So now what is machine learning? Machine learning is that we have data and their responses. Or better, I can say that features are there. So when we have data and accordingly features are available, what we could do, we can ask different algorithms to train out on this data and develop a model. On this bigger picture of artificial intelligence, as I said, that machine learning is a smaller part. On that, what we have deep learning. So deep learning is a specialized kind of machine learning process which will allow you to train data without features. But we require enough amount of data. With smaller data, we can't run deep learning kind of models. Okay. So how it is happening? As I said, that deep learning. So any of the approach, machine learning or deep learning, in both of the cases, what we require data, learn features, and then it can be predict that what is this object. Okay. And definitely, as I said, that we have enough computing power. So that enough computing power in the sense, if I want to run a deep learning model on a CPU device, it takes days or ages kind of time. So we require a GPU computing device. Or overall, maybe we require some kind of machine which will perform a high performance computation on CPU or GPU. So it totally depends that what is our need. Okay. So next thing, that what challenges industry is facing. So I'm going to talk on AI workflow, that how AI will work. First thing, that data preparation. What is data preparation? That we have enough amount of data, but whether that data is usable by our requirements or not. So we need to first prepare our data, then modeling, AI modeling, simulation and test, and that finally deployment section will come up. Okay. So again, that some of the challenges are there. So everything will come up with some kind of challenges, and we as an engineer, we are going to tackle those challenges to enhance the things. Okay. So in data preparation, AI modeling, simulation, and deployment, at everywhere some kind of challenges are available. Like might be data, what data I have some jitters in that. We need to remove out that jitters. In AI modeling, we need to figure out that what kind of algorithms are going to use. In simulation and testing, how we integrate with other, say, domains. And in deployment, what kind of right hardware we are going to choose to deploy. Okay. So how engineers are overcoming. Again, what I have a very small video of the Blue Eyesight, which has developed a complete autonomous say car, which is going to say apply a brake pre-collision or adaptive cruise control kind of things. So in this, image processing AI has been used because of it need to sense out that complete environment with lidar sensors or a complete video of that area, so that it can identify and apply brakes or speed accordingly. Okay, so this is a full-fledged autonomous system built up by Sabru Eyesight. So again, that how we are going to tackle these things. First thing first, that data preparation. So what we have automated labeling apps are available. Automated labeling apps, like when I say that we have thousands of images are available or terabytes of video files are available. How we are going to identify a specific object, like I want to specify a pedestrian in that images or a video or vehicles. So we can't say go on 1000 images or more than 1000 images or terabytes of videos and manually do those things. So we require some kind of automated things. So what this tool will do, this tool will allow me to define in first few images, first few frames, and then later on it will be automatically did by itself. So it will automatically label. Like here you see that a lidar sensor data is there. In that lidar sensor data, we can identify that where a complete car and what it is sensing around here. Or in this case, in the first image, that a car has been identified. So we can define by automated labeling. Or when we say about AI algorithm, so what we have variety of different algorithms are available. Pre-built algorithms are available. We can use pre-built algorithms to define or train a specific model. It could be from machine learning. It could be from say deep learning. Some pre-built models are there. So ready models are available. You can use those models, or you can do a transfer learning. Or you can use multiple reference examples, which has been used by industry. Or what we could do, we can import and export other networks from different vendors. Because of we support ONX, Open Neural Network Exchange. So it will allow us to say import all those networks. Like you, if you have worked, you have seen that PyTorch or Keras or MXNet. These kind of networks are available. Okay, which we can easily import. Or what we could do, we can simply design our network from scratch. So this deep network designer allow you to define a complete model within this app, and then later on what we could do, we can identify if there are errors or warnings are there. We can train our data. So all those options are available after training. So like here that data segmentation is happening. So everything we can do within click kind of form. So don't need to write a code for that. Okay, so like a complete training of a model is happening on a single GPU, and when we get that result, we can use that model to further usage. Then simulation and test will come into picture. So in simulation and test, like you are able to see in this model, what we have different blocks are available. Like 3D scenarios are there, vision detector is there, vehicle dynamics are there, and sensor fusion is there. So a complete autonomous vehicle system has been shown on this particular model. So what we have, a vision detector. Okay, so on this vision detector, what we need to do, we need to implement on some kind of hardware so that it can easily detect out surrounding things. Like you see, we can say interface this model with third-party tools also. Like this is an Unreal Engine kind of say interface where you see that a car is moving and in these two frames, what it is doing, it is finding out that where I am in a lane or not, whether some kind of vehicles are in front of me or not. So accordingly, it will apply brake or increase the speed or decrease the speed. Okay. Then finally comes up that we need to deploy this thing. So how we deploy? So we have options available that we can deploy by using code generation on CPU, GPU, or FPGA kind of devices. So any of the devices can be used for implementation, depending on your need, depending on your projects. Okay, so same thing has been followed in this place also, that we can model and simulate our system, we can test early and often, and finally we can generate automatic code also. So a complete model based design approach is going to follow in this place. Then the last thing will come up, that system thinking in classroom. Okay, so again, I'm going to talk in 3 points, that how can system thinking be incorporated, how can students be prepared, and what if you have some questions. Okay, so first thing first, that how can system be incorporated. So I'm going to talk one of the students project. It's a mini drone project. It's a MathWorks competition of a mini drone, in which it's happening worldwide. So what students could do, students can submit. Yeah, students can say submit their projects and get say approved by MathWorks, and it can be published on MathWorks website, as well as that some cash and some prize has been given to them itself. So this is the project. Like what I have given a link also. So on that presentation, the link is available, or you can simply go on YouTube and find out this mini drone project itself. So what I'm going to do, I'm going to highlight few of the points. So what is this project basically? So this is from California State Los Angeles University, where students had developed a drone which is going to pick a Rubik's Cube. So you see that what they are doing, they are simulating as well as that identifying that whether it is working perfectly or not. So while simulating, they can check out that also. So this is the actual one where it is going to pick a Rubik's Cube with a claw, which is a customized kind of claw. So why I have taken this kind of case study, or you can say that this particular student project, because of this is a very best example in which they have shown that how they are going to cover up technical aspects. In that technical aspects, as I said, that we can cover up image processing or whether control systems. So it can be covered up. Then they can find out that possible design configuration, that what kind of designs we can use. So what we could do, we can use some other CAD design tools to design out this thing, and we can import that CAD files within MATLAB to develop a complete model. And then finally, what we could do, we can design such kind of objects. In non-technical aspects, what we have, we have say projects complete say guidelines that who is going to do what kind of aspects, what are the testing things are there, in which say software or hardware they are going to use, as well as that what are the risk assessment. Like in this one of the risk assessment, whether this project will be done on a hardware or on a simulation mode. So they can simply choose out, because of both options are available. They can run in a 3D environment also, or they can run on a hardware also, that thing. And finally, what they could do, they can track down that project timeline also. So these options are available. So as I said that this project has been from California State University. So Dr. Michael Thurban has chosen some of the say these emerging trends. Like what I could do, I can show you that how a student can be prepared within this. So like what we have a MathWorks Excellence Innovation Program. MathWorks Excellence Innovation Program, in which these are the emerging fields are there, for which ready things are available. Like these kind of details are available, how you can access those things. First thing. So we have what we have variety of different self-paced online trainings are available. This is a hands-on kind of training. It is free to everyone. Whatever has been shown on the screen, it is free to everyone. Anyone can register and use that thing. Because of you are student from MIT University, MIT has already a license of campus-wide suite. So apart from this, you have full-fledged courses are available, as well as that you have access to these. As educators or students, you have access to these all courses as well as materials also. So you need to simply go and find out that MIT MATLAB portal on Google, and you can get a link where you all the details are available for this. So these all details are available, as well as that some of the virtual labs are available. So you can simply use out those kind of virtual labs. And then finally, what if you have questions? So you are going to contact us, technical support from MathWorks or a customer success engineer. So this is it from my side. Thank you for giving me opportunity.
Thank you, sir, for imparting your wisdom in this session. Now I would like to open the stage for the audience to ask questions if there are any. Anyone? Please give the mic to Dr. S.K. Sinha, sir.
Hello. MATLAB, if you haven't, most of you must be using MATLAB for your project and any kind of mini project. So that will be very useful, and sir has given a good overview of MATLAB. So how will you use this conversation as well? Yes, sir. So we must thank sir, and later on you can catch up with him. He has given his contact. You can contact us also, and this is going to help. Surely, this MATLAB is being widely used for all kind of mostly electrical, electronics, even mechanical people are also using this. So we must thank sir, and thank you, sir.
Ladies and gentlemen, and our esteemed presenters, as we draw the curtains on this enlightening session at the RDCPAE 2023 conference, I would like to express a sincere appreciation and gratitude. This gathering has been an incredible opportunity to explore the ever-loving world of electrical and electronics engineering, thanks to the dedication and expertise of our speakers and audience. To our speakers, Dr. Ian R. Peterson, Dr. Hasmat Malik, Dr. Ankur Balian, and Mr. M. Zafar, your guidance and insight have been invaluable. Your ability to steer our discussion and share your knowledge has enriched our understanding of the subject matter. We are truly fortunate to have your leadership in this session. I would also like to extend our deepest gratitude to each of you. Your research ideas and innovative solutions have illuminated our understanding of this dynamic field. Your passion and commitment to advance the frontiers of electrical and electronics engineering are truly commendable. Please join us in showing a heartfelt appreciation for Dr. Ian R. Peterson, Dr. Hasmat Malik, Dr. Ankur Balyan, and Mr. M. Zafar. Your contribution has been the cornerstone of this session, and we are honored to have had the privilege of learning from you today. We hope the knowledge and insights shared here continue to inspire and propel our industry forward. As we conclude this session, I encourage you to take the opportunity to connect, network, and engage with one another. The collaborative spirit we share today will undoubtedly lead to further innovation and progress in the world of electrical and electronics engineering. Thank you all for your active participation, and we look forward to more enlightening sessions in days ahead. Enjoy the rest of RDK 2023 conference. Thank you.